So we've gotten through all of chapter 3 of the book, and we're going to cover part of chapter 4 up to 4.4, which includes wireless LANs. And then as before, we'll, when we do the chapter 3 and 4 homework, I'll take questions from both sides. And they're really kind of the same thing anyway. 4 just expands into actual implementation. And then there's some broadband wireless and stuff in chapter 4 talking about you know, cell phone networks and so forth. And you can pick a topic out of that again. So I'll get those questions loaded up and ready, and I'll also give you the preview questions for Monday, so that you guys can look and have something to come in. So we have a bunch of things to cover today. And hopefully we're going to get through this time. We've got to cover the multiplexing, right? We did last week. We covered what was the 3 things that we got. So we got ARQ and
Stop and wait.
huh?
Stop and wait.
Yeah, stop and wait in ARQ. ARQ is really the modification to the stop and wait, where we sent multiple packets with a larger, rather than just having a flag for odd and even packets, we sent multiple packets with a byte of information or 2 bytes of information, however, and you determine that length by your network length. So now we're going to go in and talk about multiplexing. And we're going to talk about it a little bit more in depth than what we talked about in the physical layer, so that we can get some actual implementation details. So there are 2 ways that we can have multiple people talk on the same line at the same time. What are the 2 ways that we can do?
Using 2 lines.
We could use 2 lines, right? But that, I mean, we're talking about 1 line. Right? How do we
time split?
So yeah, we can split the times, right? So that's time division multiplexing. Should be a very familiar topic in computer science, because time division multiplexing is how modern CPUs work, right? They simply load up a process, execute it for some finite amount of time, save the process, and move on to the next process, right? And we have multiple cores so that you can do it multiple times at the same time. But it's very, very familiar, right? It's the whole idea of having more than 1 process run on a computer. Very few people actually use computers where there's only 1 process running, right? So what is the other way? It's more in tune with networking. And we talked about it a lot. Frequency. Yeah, we can do frequency division multiplexing. So frequency division is that I send on channel 1, you send on channel 2, you send on channel 3, so on and so forth, right? Those channels are shifts in frequency. And when you shift a frequency, right, you get all the bandwidth. So for time division multiplexing, right, you have, so we have 2 scenarios with 3 computers, right? So we have frequency division multiplexing and time division multiplexing, right? So if we have computer 1, 2, and 3, that is all connected to the same line, right? Then we have 1 send for some amount of time, then 2 send for some amount of time, and 3 send for some amount of time. And this is a lot like how your computer works, right? We simply go round robin. And then you could come up with multiple schemes if you wanted to improve it, just like queuing does in an operating system. But the idea is that you just go round robin. So 1 transmits for some amount of time, 2 transmits for some amount of time. Actually, it would be the reverse of this. So 1 sends first, 2 sends second, 3 sends third, obviously last, right? And then we keep going. And then there's some amount of guard time in between here. And then frequency division multiplexing is say 64, 66, and 68 kilohertz. Frequency division multiplexing is we send on different wavelengths, right? What's the advantage of frequency division multiplexing over time division?
You can do it at the same time.
Yeah, they can all talk at the exact same time, right? Now let's say that this time division multiplexing is 64 to 68 kilohertz. We use the whole channel to do that, right? So that we're on even playing field between the two methods, right? So in here, we can send all at the same time. Down here, right, you have to wait your turn. What are some advantages for time division multiplexing?
You get 4 kilohertz bandwidth every time it's your
You get the whole bandwidth every time, right? So here you get a third of the bandwidth, right? And here you get 100%. What are some other compares and contrasts between the two?
Can we say collision avoidance in TDM?
So we're going to talk about collision avoidance, but we can do both, and we'll talk about methods of doing that. So you get 100%, but you have to wait your turn, right? There's also some amount of loss here because we have to have some kind of guard bands between the two. There's some timing issues. TDM, right up here, if we're dealing with fixed frequencies, right, there's a finite number of machines that we can put on this network, correct? Because if our broadcast range is, we're doing 2 kilohertz for every channel, and we have 20 kilohertz of bandwidth, we can only put 10 machines on this network, right? We could put 100 on the same down here and just have degraded service, right? This is also much more flexible in that you can simply add machines. If you have some mechanism to track how many machines are broadcasting or using the network, it's more flexible, right? However, like let's say in the time division multiplexing, you get 100%, right? But only one system is using it. It's still going round robin. Right, and there's no real simple way for it to say, hey, just keep broadcasting, right? Because it's all on a timing schedule. So you could have number 2 say, I'm not going to take my frame, and so then take a smaller frame, right? And then you have some way to adjust the clock, but it quickly becomes very complex, right? And the idea is we want to keep our pipe full as often as possible. Right, and so if you look at like the frequency division multiplexing, right, is if computer 1 is sending.
Can you explain the last part with the frames? The one that you said at the bottom.
So right here is what happens if machine 2 is not broadcasting, right? You don't want the line to just sit idle, because if you let the line sit idle, then effectively you're not getting 100% of line rate, you're getting a third again. Right, and what we would like to do is keep this line as full as possible all the time. So that if you have a network that is, if you buy something off Amazon, this network that's advertised at 10 megabits, you get actually 10 megabits, right? It's not that you get half of that if you have 2 machines on it, or you get a third of that if you have 3 machines. You want most of the time the network to be full. So, in frequency division multiplexing, right, remember we talked that computers are almost always bursty, right? They talk a lot and then don't talk at all. And then they talk a lot and then they don't talk at all, right? So we have these large periods down here where nothing is being used, right? And so if we have another one, right, that's talking at some rate in a different channel, right? The idea is that we would like to be able to combine these rates. Let's see if I can make this look somewhat real, right? So high, very high, medium, very high, medium, high, something like that. Right? And then this peak rate here, it has to be less than, if this is channel 1, this is channel 2, or let's say this is A and this is B, then this peak rate C has to be less than or equal to A plus B. Correct? And so it's likely that our bandwidth, our rate is lower, and if you had a lot of computers on this network, right, it's likely that that original idea that we talked about with bandwidth sharing and statistical multiplexing can come to life, right? We can actually implement something that allows us to over-provision this network so that the pipe is mostly full. Right? So then the question is, how do we achieve this? Frequency division multiplexing doesn't do it, right? Because we divided our line in thirds, right? And it doesn't matter how much of a fraction you do, right? The idea is you want all of these not to be a third, but somewhere near 1, right? We want to over-provision our network. This doesn't work either, because it becomes very complex on how do you tell two and 3, if 2 and 3 are not broadcasting it at that time, how do they alert number 1 that he can broadcast all the time? Right? And then when that situation changes and 2 needs to talk, how does it alert number 1 to shut up?
We can use the statistical, the STDM.
So statistical time division multiplexing, right, is what we're trying to achieve, but time division multiplexing doesn't really achieve that, right? Because in a computer, time division multiplexing works well because the operating system is managing everything. So the operating system can go to a process and see that the process is asleep, and then just leave it. Right? Because you have this grand scheme. A network is not an operating system. There is no thing that's sitting in the middle telling each computer how to work. Right? It is a completely distributed system. So we need to come up with some other algorithm that allows us to fill that pipe, right, when other computers are not talking, and then and then some way to interrupt to say, hey, I want to talk, right, when another computer needs to. And neither one of these fulfill it.
So this means the FDM and TDM waste some bandwidth.
The FDM and TDM do waste some bandwidth, but they may be good on backbone systems. So frequency division multiplexing is used in cable modems, right, because you are broadcasting TV in some spot. TV is an always-on technology, right? And so frequency division multiplexing is used in broadcast media. It's used in TV, it's used in FM, AM radio. It's all the same thing, right? Because it's always on. So there's no time when classic rock 98.1 tells 99 or 99.9 to shut up, right? They both go at the same time, and they just are always on. So it works well in that scenario. And in blended mediums, like cable modems, right, they're still sending the TV signal, and they're using some other bandwidth over here, right? But that bandwidth, even though it's frequency division multiplexing up there, we're going to use that bandwidth in a different way. Right? We are going to tell computers to shut up. So, how do we go about doing that?
So what if we hybridize the two process, FDM and TDM?
So remember, you can. So what we're going to use is we're going to use, like for a cable modem, we're going to continue to use FDM. But we want something that's very similar to TDM. But we want a computer to be able to fill that pipe. And the question is, how do you achieve that? So let's take a look at two different methods. The first one, we're going to do a randomized multiple access.
So this one's chapter 4, right?
Huh?
This one's chapter.
This is chapter 4.
Okay.
And we're going to start with a very simple Aloha protocol. So the idea is if we have multiple computers on a classic broadcast network, right? They all share the same line, and there's nothing managing anything in between. How do we solve the situation where one person wants to talk, one person is free or asleep, and another person is free or asleep? And we'll just say slow. It's not doing much of anything, but it might. Right? This person wants to talk, but it doesn't know if these are busy or not. How do you solve this situation?
So can we have each of the computers listen on the line before we start sending?
Yes, we can, because this is not a wireless network. Right? We talked we can't do that in wireless, but in a wired we can. And they can also listen while they're talking. Right? The difference between a wireless is you can only listen before you talk. And on a wire you can listen while you talk. So in this wired network, how do we could just send a message out, right? So this one sends a message out, right? And that message is a packet. And the packet goes across the network, right? Let's say that it's going here. Doesn't really matter. So the scenarios is we listened to the network, nothing was there, so we sent it, right? And it reaches its destination because nobody else talked, right? That's our ideal situation. The other one is somebody else talked and we have a collision. So let's say even though B is getting it, so this one has sent and it's on the way across the network, this one is sent, right, and it's on the way across the network and they're going to collide about there. How do we know if it's collided?
What's the time?
There's no acknowledgement, right? We send an acknowledgement. We talked about this, right? We do a transmit and we acknowledge. We do a transmit and we acknowledge. Right? So then our collision comes, so for this diagram, right, we have sent and there's a collision, so the acknowledgement doesn't exist. And that's pretty easy, right? So now let's look at like what a multiple network looks like and see, let's take a view of how this thing would actually function. So if you had a network, okay, with multiple computers on it, right, and they're all sending packets, at just random times. When you want to send, you just send. Right? And then we wait for acts. What's the problem right off the bat with this? Where are our collisions? right? It's anything that's lined up. So these three packets collide, right? And all three of them are trash. This packet collides with this one, and that is also trash, right? Let's put it actually in the boxes. So trash, 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 and trash, right? And this is the only one that gets through. So you can see that in any network that has some kind of congestion, this is probably not going to function well. And in fact, if you do a statistical analysis at it, I believe it's like 18%. If you have such amount of bandwidth on a line and you fill it more than 18%, then this starts happening. So what's the easy solution for that?
Sure that didn't go above 15%.
Well, we could easily, sure, right? But you see that this one isn't a good example. Let's say that this packet was more like this, right? And it just barely clipped it. What if we added timing to the network? Right, so that if you had some kind of timing mechanism, you have, instead of packets going out randomly, right, you have a scheduled timing where you can send packets. Right, and so then A sends a packet here, D sends a packet here, they both become trash because they send it, right? But there will be no almost made it. Because almost made it is still trash because it's just going to come through as errors. Right? So we could do this, and if you do that, then you can up the performance to double 18%, so 36%. And you can see why we would double it, because if you look at what we were doing before, right, the median time to overlap a packet is 50%. So if you take that away, you double it, right? But you're still going to have collisions, right? And you can only get 30%. But it's super simple to implement. And this is essentially what the Aloha protocol was. So Aloha was the islands in Hawaii wanted to talk to each other, and it's over wireless, right? So you can't listen while you're talking, right? But the idea is the same. Hey, if I don't get an act, something happened, right? And then send again. So, and that's how they achieved the 18%. And then on things where you can control timing, you have a very accurate clock, or you have some kind of synchronization protocol happening on the network, then you can up that to 36%. But that's still not 100% of our line.
Is it always 30%?
Huh?
Is it always 30%?
So for random access, 36% is as good as you can get. So let's take a look at wireless, and that will lead us into contention free. before we do wireless, let's cover, CMA. Before we do that, let's. Let's look at our same network. So, we're going to talk about carrier sense multiple access, which is a current implemented protocol. It's an Ethernet. It is good for things where it has a broadcast medium that is fixed, so not anything that's wireless. So we need to be able to listen. And we need to be able to listen while we're talking. So Aloha isn't good because we can have packet overlap. So the question is, how do we fix that? And it turns out the answer is not actually all that difficult. What we do is we send packets that are the full width of the network. So if this guy sends a packet, that packet is the entire length of the network. That means that if this guy is sending a packet, by the time the packet ends here, it's already being received here, and everywhere in between they know that there's a transmission because they can listen to the network. Now, of course, it is possible that he starts sending a packet at the same time that somebody else starts sending a packet, and then it is collided, right?
Mm-hmm.
So what we do is, if there is, and this, by the way, is only good if the distance and bandwidth product is small. Right, so we can't do this for long-range networks, because if we sent a packet that was the full length of here to New York, right, that's a lot of data, right? And then even if we did implement that, then a collision is very expensive. Huh?
Yeah.
Yeah, we've tied up an entire line, right? So, and while it does seem like a short distance at the speed of light from here to there, right, is still a lot. And if you tie that up, then you're not going to get the performance of your line. Right, but if the bandwidth, all right. So in Ethernet, we have a very small fixed distance that we can have between, even in modern Ethernet, it's between switches, right? So the lines can only be a fixed distance, and that fixed distance is pretty small. I believe it's 323 feet. Don't quote me on that, but it's pulling out of very old memories, right? But it's pretty small, and the idea is that it's fixed and it's small, right? So then, if we know that this is the max distance, then we can calculate based on the bandwidth of the line how big our frames can be, right? And with the original Ethernet standard, those were 64K. If you ever want to know why frames were 64K, that's why they were 64K. So they would fill up the line between one point and the other. And the number's not important, right? But that's not where these crazy numbers come from. Is that it isn't that we needed frames, arbitrarily the size. That was the size for the thing to be completely full. And so if we do that, then we only go ahead.
So it's called is that the MTU, or is the MTU something different?
No, it's MTU and Ethernet, yeah. Okay, for old frames, it's actually just 64. for really old Ethernet. So for really old Ethernet, which is the kind on coax cable, then it was just 64. But that was the idea, is that we could fill it up, and that was basically 64 was the frame for 2D seconds. So the distance multiplied by 2. Why do you think we do the distance multiplied by 2?
Round trip time.
Because we need a round trip time, right? Let's say that this thing almost gets here, right? And didn't quite get here, right? And this guy started broadcasting a frame. And so the collision is right here. So we need 2D time, because this is the time that the act should have been received here, between the two. Now, what we do is, what happens if we do have a collision?
Cancel out.
So both nodes will know, actually every node on the network will know that there was a collision. Because remember, this is not a switch network, this is just a coax cable. So every node on the network will know there's a collision because they got to listen to it. So then the question is, how do we negotiate who gets to send next?
It's just random time.
We add a random time. And what should that random time be? Well, it really depends on how many nodes are on the network,
Okay.
right? So in this one, we have 3 nodes. So ideally, our random time would be 0 time, so somebody gets to transmit immediately, right? And then an increment of 1 or 2. And if we do that times the distance of the network, right, the time it takes for light to travel down that network, then if we do this, then and we had some way for one guy to pick 0 and only one guy to pick 1 and only one guy to pick 2, then it would immediately work, right? Of course, we want a distributed system. We don't want somebody to manage the network. We want them all to be able to manage themselves. So we could just pick a random of this, and then sometimes, you would get 2 guys picking 1. And 2 guys picking 2. But this still is still managed because we need to know how many are on the network. Go ahead.
So this is analog, correct? How does it know it's detecting an error? How does?
So because everybody is receiving all packets on this network, because all packets are being transmitted on the line, so they can simply listen even if it's not their address. Right, so imagine you put, for the guys that have done IT, you put your NIC in promiscuous mode, right? And so it's just listening to everything on the network, right? So this is still happening, it's listening. And it's listening and it's really only checking checksums to see, or checksums or CRCs or whatever we're using to make sure these packets, and then you'll be able to tell there's a collision because it will be completely unreadable. So we could pick some number of 1 over n for the number, but that's still managed, right? It means every time that you add a node, then you have to go reconfigure every other node to be able to pick n. Well, we could make a protocol to say, hey, occasionally announce yourself to the network so that we can figure out how many n's there are. And you could do that. Announcements actually happen all the time on the network. Right, but that's still not ideal. So what we could do instead is a technique called binary exponential backoff. which is a really complicated thing for something that's super simple. So, remember, everybody can hear how many collisions are on the network, because this is not a switched network yet. Hopefully we get to that today. So, you do an algorithm that says every time the first time there's a collision, n becomes 0 or 1. And then the second time there's a collision,
You double.
we start doubling it. Correct. Right? It becomes 0 to 3. And then the third time would be what? 0 to 7. Because we start doubling, right?
Oh, 0 to 3. It's not, should be 0 to 2, right?
Yeah, it's 2 to the n minus 1. Right? So this becomes to the first n minus 1, to the second minus 1, to the third minus 1, and so on and so forth. You can see this n would get very big very quickly. Right, so while it would be super inefficient, the first couple of collisions, right, it would rapidly become very efficient. And since this is a network and we're dealing with milliseconds, right, there would be a short little burst when you add, if you added 10 machines to this network and turned them all on, there would be a short little burst of the network degradation, followed by it coming back up and hitting somewhere, you know, you never get 100%, but it's close. And this is classic Ethernet. The old kind with coax cables. Anybody deal with that back in the day? No. But we're getting really close to something modern. So modern Ethernet isn't super different than this. And there is some confusion because they're both called Ethernet. But we're actually into a real, actual standard, the 802.3. And we should be able to have enough knowledge that, as a class, hopefully we can fill in each other's gaps and be able to architect that. So the Ethernet frame that actually implements all of this So we have a header, and in the specification it's called preamble, but that's exactly what we've been talking about this whole time, right? Is some way to delineate the beginning beginning of the frame. Right, remember this thing gets stuffed in this side first into the network, right? So the header goes in first, and then we have a destination because we are going to need that. And we don't want every computer to have to read every single frame, right? So we have a destination because it needs to know right off the bat, is this mine or not? And then we'll need a source so that we can return packets in this network. Later on, we will use this source to do switching. Type is what kind of standard we're actually using. It's usually a version, right? So we've been talking about very classic Ethernet here. The data, which is this small little spot, but it's actually much bigger, right? Because all this stuff over here is just a few bytes, right? And we have a 64-byte frame, right? So the data is much bigger. There's some padding. Why do we put padding in there?
It has to be linear, so it has to be divided by 8, something?
Yeah, well, we want to divide it by 8 for sure, right? But why do we put padding in files, or in this case, frames?
Consistent size?
Yeah, that he's correct. You are correct. A consistent size, but wouldn't it be just better to fill this with data if we wanted a consistent size?
Security?
What if you-
Yes, kind of.
What if you left room for future?
Room for future improvements. One of those improvements might be security. Right, we have built part of the link layer is implemented in the physical, like the electrical engineering part of the engineering work, right? So some of that stuff can't be changed. And if it can't be changed, i.e. the length of the packet can't be changed, it's fixed as 64, we want to keep some space in there for future improvements. And it's done frequently. You'll see it all over the place, right? It'll just say padding, or you'll see like a data standard where it's like you have all these bytes 0 through 5 and 5 through 8 and 8 through 16, and then you'll have 40 through 44, and there's this big nothing there, and they don't even explain what's there. It's just padding for future improvements.
Question, what does it say on top of XDR?
Preamble. So in the specification, it's actually called a preamble, but it's just the header, like we've been talking. Just another name for header.
So for the header, we can actually add new things to the header, like for instance.
We could change the header, provided that it is not part of the physical layer. But I can tell you that in classic Ethernet, that header is in fact part of the physical layer. Remember, I said that there was things, why do we implement the link and the physical together? Right, because there are certain things the physical layer can do that the software layer can't, right? Like send a very specific signal. So if you remember, if you had like our steps, right? You could reserve this top step, right, for framing. So that this header had some framing that was implemented in the physical layer.
Is the pad still available?
Yeah. If you want to get yourself a really old NIC card.
It is required by some protocols, right?
Huh?
It is required by some protocols that we have to have that.
Well, it was built into the specification, right? So when they built classic Ethernet, they thought it would be around forever, right? Because, well, if you looked at it from back that point, why wouldn't you think it had been around for? It was around for a really long time, because you had to actually run wire in through your building, and in this particular case, it was a single wire that you snaked through the floors, right? And the NIC on the back of these things, if you guys, nobody said that they've actually done it, right? So it had what looked like, kind of like the cable port on the back of your TV, except for it didn't have threads, right? The cable port kind of looked like this with two little buttons on the side, so that you stuck it in and you twisted it, and it just stayed, right? And then this thing had things like this with the same things on the ends so that your coax cable would run in. And you get one continuous coax cable. And if you had a new computer, you would literally cut the cable, kill the network, right? And put your new NIC card in. Now, of course, this is just coax also, so your NIC card could actually be down here. And then you could run coax here and cut your cable. Right? But the idea was the same. And I think I might have one of those at home. And if I do, I'm definitely bringing it.
Isn't it bigger than vampires? I'm thinking of something like
Yeah.
that actually just jabbed in.
Yeah. So then there was vampire taps, right? Instead of cutting your cable and putting it in there, there was this thing you actually crimped on your line.
It would pierce the shield.
And it would pierce the shield, right, and put like a jacket around that, and then there was a vampire tap in there, because a coax cable looks like this, right, where you have a copper wire followed by some kind of jacket, followed by some mesh.
Grounding.
Yeah, well, it was that, and it's also a Faraday cage, right? So it keeps signals from going in. It's a shielding. And then you had, around that, you had a, some kind of plastic, right? And so then what you would do is you would get like this vampire tap, right? Where there was something sharp, right? And you actually pierce that thing, and it allowed you to tap into there. But the idea is the same. You have a cable, and you literally are physically messing with this thing. Not very similar to what we have today, which is you just run a wire and plug it in. Why doesn't this work with wireless?
Will not be able to receive, will not be able to listen.
Yeah. So you can't listen while you talk. Right? So if there was a collision and you were talking, which was our first example of a collision, you wouldn't hear it. Right? The other thing is that in this kind of network, every node gets to hear what every other node says. But because of the law of squares, when this guy broadcasts, this guy might not hear, even though he's in the same network. And you could easily visualize that this actually could happen if that was the access point. UCCS's access point, right? You guys are both on the same network, correct? But this guy here, if he broadcasts, this guy will hear it. This guy is deaf. He can't hear it. That becomes an actual problem. So we could do some kind of transmit and acknowledgement scheme, like we did with the Aloha network, and do a transmit and then followed by an ACK. The problem is that if this guy transmits and this guy acts, this guy won't hear it. So because this guy doesn't hear it, he doesn't know. He heard the transmit, didn't hear the ACK, so he's expecting another transmit. That's what you do. Right? You transmit, if you don't hear an ACK, something happened, you transmit again. And this guy is never hearing the ACK, so he is always waiting. It actually becomes worse if you add another one in the network. So now these guys could be talking to each other. And these guys are talking to each other. And that is fine because this guy can't hear this guy again. Right? But in a transmit in an ACK scheme, right, this guy is hearing all the transmits. He's hearing the transmits from this guy, the transmits and ACKs from that guy, and no ACKs from this guy. So how do we solve that?
Just get closest to each other, make clear, access.
Yeah, what we would like is for them to be able to transmit and we like some scheme where if they are transmitting, they can transmit and it doesn't rely on an acknowledgement from somebody he can't hear. So we can't do our simple, we'll still use that for when A and B are talking. We will still use transmits and ACKs for them talking. But we need to add something else so that if this guy, who can also hear this guy, knows that when he can talk.
Through hops?
But there's no hops, right? Because this is a mesh network-ish, right? Because we're just broadcasting out into the air.
Would the access point itself have some kind of management?
Well, it could be the access point, and it's frequently, normally, in 802.11 anyway, computers can talk to each other, but it's actually called ad hoc and it's a giant pain in the butt. Right, because they weren't really set up on that. Now today, that's actually changing. Who has an iPhone? How many people have used AirDrop? How many people know how it works? Huh? It uses wireless, right? It uses wireless to wireless, right? And Bluetooth.
It's like Wi-Fi Direct kind of? or-
It's like Wi-Fi Direct.
Yeah.
And since N is on both 2.4 and 5, right? And iPhone the newer iPhones have both antennas. It simply shuts off one antenna for Wi-Fi and uses that for the AirDrop before turning it back on. And then it uses Bluetooth as the negotiation channel.
So they do this both.
Yeah. Wi-Fi to send data, Bluetooth to negotiate. Right, so when we talk about, okay, well, we always have access points in Wi-Fi, that is rapidly changing. And it's changing and we're not even paying attention to
But
it.
do you think it just depends on the Wi-Fi that you have when you're doing an airdrop? Because it seems to be a little faster than most other things.
Well, normally, because you're very close,
Right.
right? And you guys have negotiated a channel in between yourselves. So there's in an AirDrop, there's no other computer sitting on your channel other than some guy off regular noise, right? But you only have a peer-to-peer network and there's only 2 peers. So you don't have this multiple contingent access, which is what we're trying to solve here, and you'll see why Wi-Fi is slower. So what you do to solve, really you have 2 problems. You have a problem called hidden terminals, which is what we've been talking about, where A talks to A and C are both talking to B, but A and C don't know each other exists because they're too far away. Then we all have another problem called exposed terminals, where A and B are talking, and C and D are talking, which is totally fine because A can't hear C and B can't hear D. Right? But in our traditional transmit and ACK, it is a problem because they cannot hear the ACKs. So what we do instead is we consume a little bit of bandwidth. And how we do that is we do a request to send. So, like at the beginning of the class, I talked about, hey, how does a human work on the radio, right? Normally, if you're a cop, and I was a cop at one time, you jump on the air and you say, 1M61 traffic, which is me, and I'm about to pull somebody over. And then dispatch comes back and it says, 1M61 go ahead, which means that I have the air and I get to call out my traffic stop, and everybody else obeys the rules and doesn't step on me. Because if they step on me, nobody can hear anything. So we want to do pretty much the same thing, right? We want A to say something like A traffic. And we want B to say A go ahead. So there's only, in human communication, I didn't say, hey, when I say 1M61 traffic, dispatch and everybody else who's also a cop knows how long about it's going to take me to talk. Right? I just call out my location, I call out the license plate and description of the vehicle, and that's it. So we do something similar here. We say, A traffic, and then we say how long we're going to talk. And then B says, go ahead, A, this is how long I acknowledge you are talking. This is important because C never hears A talking. But C will hear that B says, go ahead, A, you're going to talk this long. And that way, C knows not to talk to B for that long.
How does B knows how long A will talk?
A tells him. So we say a request to send. And we're gonna request to send with 64 bytes again. And we're also gonna say, hey, we are A, and we are talking to B. So B, this is a request to send 64. And then B says, you basically go ahead, right? So it would be A, B, go ahead, right? 64. So this message is received here also. Now C knows not to talk to B for 64. Now the question is, can C talk to D?
Yes.
Absolutely. C can talk to D. Even while B is talking to A.
B can still hear C.
And B can still hear C, that is fine. And we're not stepping on each other. Because when C transmits, because he can't hear A, he knows that somewhere around here the signal attenuates so far that it no longer interferes with their communication. If B was talking to C, right, the signals would be somewhat the same. So, yeah. So if B is talking to C, right, the signal attenuates this direction, right, and it attenuates that direction, and right, so they're stepping on each other. So even though C is communicating on the same channel at the same time, which normally would be stepping, right, it attenuates so much that it no longer, by the time the signal reaches A from B, it no longer matters. And then C can talk to D. And it deals with, it solves both problems.
What was that? You said that it doesn't matter?
Huh?
If they step over each other? Or
It doesn't matter.
Okay.
So it only matters if C is talking to B and A is talking to B. Then it would matter, right? Because the relative strength of the signals are the same. But that would never happen because B acknowledged, hey, I am going to talk to A. And so C shuts up. Now we have to listen for acts, So we have a request to send of 64, which C could step on that and not hear because C when they're talking, right? But we can still solve that just the way that we did before with acts between B and C. Because if C wanted to talk to B and said, B, this is C, request to send 64, he would not get an ACK. And so what you do is you lay off a random amount of time, and then you try again. So here comes why Wi-Fi sucks when there's a lot of people on it. I lay off a random amount of time. This network there is no way, remember before we just filled up the network, everybody could hear, because everybody can hear while they're talking, how many are on there. Right, and so when we're talking, if we do like exponential back off again, right, that time rapidly grows, and we can't listen while we're talking. So there's more of an impact when we delay. So our frames need to be shorter, not longer, because we can't listen. Right, and the more that we get on here, that we get rapid degradation of the network.
So, is it what the request and response like broadcast it to everyone, or just like this is just an ad hoc network?
So, in a sense, it is ad hoc in the physical layer. So in the logical layer, it's not ad hoc. You're talking to an access point, right? In the physical layer, it is ad hoc because everybody else can hear everybody else. There is no segregation of the network. And it's not possible to segregate it, right? Because you're simply broadcasting things in the air. And it propagates out in a bubble. And everything that gets in that bubble is inside the sphere of influence of that radio. And the channels are already messy to begin with. We've talked about that. Go ahead.
Could you explain hidden terminals again? Which ones communicate?
So a hidden terminal is where in this situation is where A is talking to B and B is talking and C is talking to B.
Okay.
That's a hidden terminal. And then the other one, which is exposed terminals, is when A is talking to B and C is talking to D, which should be fine, except for in a transmit ACK, you never hear the ACK, so you're always waiting. One guy's always waiting, right? So the request to send solves that by consuming some bandwidth to be able to get an acknowledgement that you can talk. Now, there still could be collisions in the request to send, right? That's why we keep the request to sends very small. If we keep them very small, there's less chance of there being overlap. Of course, when we grow our network,
Until you get too many people.
you get too many people on the network, right? And you have very chatty devices, like all modern devices are very chatty. If you ever jump on Wireshark and look at it, they're very chatty. Right, and so you see things going across the network that are just background processes just filling the network up. And so when you put a bunch of devices in a single room, you start running into issues because, not because they can talk, because they can. They can talk at full bandwidth, right? But you need the acknowledgement that you can. And if you keep stepping on each other and you never get an acknowledgement, then you never get the bandwidth to talk. And that is 802.11. Hey, we covered our first modern thing.
So in the case of RTS, it means that we will not be dealing with a loss of data because the RTS is like a control message.
It is a control message,
So
yes.
it's being sent without an acknowledgement. The node might as well back off for a while.
Yes.
And then try.
And then try
without
again.
losing any.
Yeah. And we try to keep those very small, right, so that the bandwidth of the network isn't being, because we expect there to be collision. But you recognize that in this scheme, unless you have a node that is not playing fair, right, and we haven't talked about security issues yet, if everybody's playing fair, it is not possible for you to step on somebody else's transmission in this scheme. Because you had the error. You did a request to send and you got an acknowledgement, you get to send. The only little caveat becomes is that we did this all very static, and in mobile environments it's actually not static. People are walking around with their phones, right? But you could just, those are just other problems you just overcome, right, when you're writing in the standard. But this scheme actually works, and this is how 802.11 actually works. So let's take a look at what that's right. That's good. Some things are timeless. So this is the actual data packet. Again, data is actually much bigger, right?
Oh, no padding.
So now we have a header, and in the spec it's called control this time instead of preamble. It's the same thing, right? Then we have a duration. Why do we have a duration?
How long are you gonna take?
Because we just said that we had to have some mechanism, right? So, hey, this packet is in fact the duration, right? Now we have 3 addresses. Why do we have 3 addresses?
It's in for each layer, layer 1, 2, 3.
It's not in layers. This is only in the link layer.
One's for the access point?
One is for the access point. One is for the access point. So in 802.11, right, we normally talk through an access point. And when we normally talk through an access point, we need its address also. This is not its IP, right? This is its network address, its MAC address. So we need it, we need to be able to identify it. Why?
To get a packet to somebody else through them.
Yeah, well, to get a packet through somebody else, and there might also be more than one access point. So think about how 802.11 is actually implemented in this building, right? They have a wired network that is through this building, and there are a number of access points here and here and here and here. They necessarily have to overlap with each other, right? Because you don't want to walk and there'd be like a 3-foot dead space before you get to the next access point, right? They overlap. So there's a possibility that right now you could be talking to one of 2 access points, right? And we don't want to really care, right? So as you walk through in the spec, it says, hey, just pick the one with the best signal, right? Measure the signal and use that one, right? And this is not in the IP layer. This is in the link layer. So there's a MAC address.
So it means that before a node can send any message, it needs to send out like a control message to find that.
Correct. There are control messages to say, hey, I am working with this access point, right? And also recognize that a lot of this stuff is encrypted. So there are some things that probably aren't well encrypted, right? Like the header,
Test.
right? Because we need to be able to identify a frame, but most of the other stuff is encrypted. And we add that layer on top of it. But we don't really need to think about that right, is that there's an encryption layer that's transparent to us. And then because we are all working in the same encryption scheme, we can simply read the packets as they come through. So, the last thing for, this is carrier sense multiple access, just like before, but this is, instead of, the last one was, when we were doing classic Ethernet, was carrier sense multiple access, and then it is CD. What's the CD stand for?
Collision detection.
Collision detection. This is the same one, this is CA. What does CA stand for?
Collision avoidance.
Collision avoidance. So the question is, if our message, our request to send gets stomped on, what is our delay factor, right? So that we can broadcast, right? And the delay factor in this is called a back off. And so if you have A, B, and C transmitting, this is time this way this time. You have A, B, and C transmitting, right? A is transmitting to somebody, and this, so you get an acknowledgement out of it. And there was some collision that happened before. Was what you do is, if B and C were tried to transmit and there was already a collision, right? They get some random number. And that random number is called a back off. And so let's say part of that random number was here, and it started counting down, right? And because there was some collision that happened back here. And then A started transmitting, and B hears that, because it's sitting idle in a random number, it simply pauses the random number ticking. So now this is random number minus whatever time elapsed. And then at the end of this frame is random number minus time again. And it will start transmitting. B does the same thing, but since it picked a different random number, maybe this one's a little bigger. And if there was some time that it was also idle, right, it would be minus that time. But it's bigger, so now the remainder, the difference is bigger, right? So, and then it will hear this transmit, right? So right here, it will pause again. It will pause doing its timer, and it will start doing it again. That's how the back off works. This is also how a very congested network becomes a big giant pain in the butt.
So in this case, what's going to happen if it keeps?
No, no, fine.
Hi, it's Tom.
Sorry.
Mhm.
So what's going to happen if, say, A continues transmission, and B had already chosen a random number, and for every time A is broadcasted, the random time stops, right? And is it possible for it to go on and on and on and lead to like a serious latency issue in the network for B?
So at the end of this random time, like let's say that A starts transmitting here, right? And these are close enough where B can't actually hear that he's transmitting, right? And there is a collision here. Then A would take a random time, right? Now you get this full Remember, this is an RTS packet though, not a data packet, right? So it's small. Let's say just overlaps that thing. Right, now A would take it back off, right? And then the back offs would be longer than the packet, so that there's never, A can't consume the entire network and always be transmitting. If you're playing fair.
Well, then wouldn't B have to retransmit since there's a collision, and that's just gonna keep spreading out the.
Correct. Yeah.
Okay.
Yeah. All right. So on Monday, we are going to cover switched networks, which is actually not all that hard because we actually have the basis of Ethernet. We will see that there's no reason for collision detection in a switched network at all. Because a collision detection, a collision in a switched network is not possible. But other than that, then we'll do a very simple switch network. So maybe 8 years ago, where you couldn't put loops in it unless you bought a really expensive switch, and then we'll talk about those really expensive switches, which are also modern switches, which do have loops in them, and how that actually works. And I will send out the questions, and we will get to probably a couple of the questions, because I expect to only take 15 minutes or so to talk about switch networks.
Like ARP storms and stuff, is that what you're talking about?
Yeah, yeah. So ARP storm, when you had left the old switches, like about 8 years, maybe 10 years ago, right? If you looped it up, you get an ARP storm.
Yeah.
You don't get that.
I experienced that one firsthand because we were like quickly throwing together a network, and then someone was like, "Well, there's this cheap switch. Let's throw this in there." Somebody went ahead and ran a second cable to it, and then all of a sudden it was like the network just shut down. And it was like,
It shuts down your entire network.
Yeah.
Modern switches don't do that.
Right.
And the expensive ones didn't do that either because it's not a new idea.
Do you want this unplugged?
Yeah.
Okay.